Hello guys, today I'm with you, Elias. We will be discussing Discrete Structures Homework 4, They gave us 3 sections, 4.4, 4.5, 4.6, questions 5, 6, and 9 for the first section, 5, 6, and 7 for the second section, and 2, 3, and 4 for the third section. So we'll briefly go over the first section just because it is going to be over the Euclidean algorithm and finding the Byzantine coefficient. I know enough to work it out. I understood it, but not enough to explain it very well, so I don't want to confuse you guys. I'll show you guys what I got, and then we'll go from there, and then I'll actually go on and to explain sections 4.5 and 4.6. So let's hop on over. So actually we'll go over here. I'm not sure if you guys can see this. Let me make this a tiny bit bigger. Boom, that should be better. So right here on section 4.4 we have questions 5, 6, and 9. So questions 5 and 6 are very similar. They both find an inverse of A modulo M for each of these pairs of relatively prime integers using the method followed in example 2. Then question 6 says find an inverse of A modulo M for each of these pairs relatively prime integers using the method followed in example 2. So worked much the same. And then question 9 says solve the congruency of 4x 5 mod 9 using the inverse of 4 modulo 9 found in part A of exercise 5. So we'll hop right in. I'll give you the view of my paper where I worked it out. And here we see that I have question 5 right here. So we started with question 5, Euclidean's algorithm. It gave us, you have to find the Byzantine coefficient of 19 mod 141, which to do that I kind of set this here. 19 times what number gets us close to here, and what is left over is practically this explained. I'm not going to go too much into that just because I told you guys I know enough to work it, but not enough to explain it too well, and I don't want to confuse you guys. So here's what I got. Byzantine coefficient equals 52. On 5a I got the Byzantine coefficient of 7, which is right here. There's other parts to 5, so let me find that. 5c got the Byzantine coefficient of 34. 5d got the Byzantine coefficient of 73. We hopped on over to C, worked much similar or the same. Over here, 6a, I got Byzantine coefficient of 9. And negative 8 is our inverse of 2 mod 17. B, Byzantine coefficient is 55. Hopping over to C and D. C, Byzantine coefficient of 89, and D, Byzantine coefficient of 996. We'll hop on over straight to chapter or to section 4.5 where we were talking about pseudo-random numbers. I'll go ahead and switch screens so I can show you guys what the book had, and then we'll come back to my answers. So hopped right over. So go to page 313 really quick. So I'm on page 313. The questions were 5, 6, and 7. So we start with 5. What sequence of pseudo-random numbers is generated using the linear congruence generator x n plus 1 equals 3x of n plus 2 mod 13 with seed x of 0? So questions 5, 6, and 7 are all similar, but they give us a different congruential generator, linear congruential generator for each one. I'll go ahead and hop on over to my work. So you can see we were given this example right here. So The sequence given to us was 7 x of n plus 4, and we use what they gave us, x of 0 equals 3. So to find x of 1, we would do 7 x of 0 times x of 0 plus 4 mod 9. So this would give us 7 times 3, 21, plus 4 mod 9 would give us 25 mod 9, which ended up being 7 right here. Very similar to what question 5 was, but instead we use this linear congruent thing that they gave us. And this time they gave us 3x of n plus 2 mod 13. So they gave us x of 0 equals 1. Over here I have my x of 0 through 3. And why I stopped at 3 is because once it gets to the number that it began, it's just going to continue repeating. So I only worked through x of 3 because after x of 3 would come x of 4 would equal 5, x of 5 would equal 4, x of 6 would equal 1. It just repeats over and over once you get to that initial value. So here's my work that I showed. 3 times the x of 0 is 1, 3 times 1 plus 2 equals 4, oops, no 5, sorry, 5 mod 13, you skip on over here, 5 mod 13 gives us 5, so x of 1 is equal to 5. Now we use x of 1 in the second equation, so because to find x of 2, x of 1, we would have to use x of 1 because x of 1 plus 1 would equal x of 2. That's how we get to this and use this over here. So 3 times x of 1 is equal to 5. So 3 times 5, 15 plus 2 gives us 17. Mod 13 comes out to this value of 4. And I worked it the same here, which gave me these answers over here. Number 6 worked the same, except they give us this function instead of the one we used before. Same thing, they gave us x of 0, which is equal to 3. We just have to plug it in because we want to find x of 1. To do that, x of 0 plus x plus 1 would give us x of 1. So we substitute x of 0 right here. 4 times 3, 12 plus 1, 13. Mod 7 would give us 6, as we see right here. Worked it the same here, but used an x of 1. Worked it the same here, but used x of 2 in the place of x of n to give us this repeating pattern of 3, 6, 4, 3. So x of 4, the continuing one, would be 6, x of 5 would be 4, and then x of 6 would repeat to 3. So it just keeps on repeating after you find the first initial value. Going on to question 7. 7 did take a little bit to repeat, but ended up repeating after 5. So it gave us x of n plus 1 equals 3x of n mod 11. So we used x of 0 to find x of 1, because x of 0 plus 1 equals x of 1 again. 3 times 2, which is x of n, would give us 6. Mod 11 would give us value of 6. So we went on, used for x of 2, we used x of 1, for x of 3, we used x of 2, for x of 4, we used x of 3, so on and so forth. And that's how we got these numbers on the right, by plugging them in to this congruential linear function that they gave us. So once you get to that initial value, they will repeat. So like I was saying previously, x of 6 will be the next one after, which is 6. So x of 6 will equal 6, x of 7 will equal 7, x of 8 will equal 10, x of 9 will equal 8, and x of 11 will come back to be the number 2. So that's it for 4.5. On 4.6 we talked about Caesar's shift and shift cipher, which you see here on my page. I'll go ahead and show you what the book has, and then I'll come right back to my work. So our section 4.6 started on page, I have right here 325, so I'll go ahead and hop on over to that page. Practically what shift cipher does is that it assigns a value to a letter of one less than what it is. So if it's A is the first letter in the alphabet. So we would shift it down back 1 to 0, and that's the numerical value that A would have in order to proceed on to Caesar cipher or shift cipher. So what is done is that value that we get is then shifted by the amount that we have here. For example, I do question 2, right? So it shifted 4 values on A. So A would no longer be in place 0, it would be in place 3, if that makes any sense. I'll go ahead and show you guys my work, and oops, I didn't even go over the questions, but yeah, so we have to encrypt messages, stop pollution, watch your step, because we do questions 2, 3, and 4, and decrypt these messages over here using Caesar's Cipher. So Caesar's Cipher only shifts the value by 3, so that's how we know what to use, what function to use. So we'll hop on over to my work, and I'll explain it as I go. So like I said, right here, I have my stop pollution. I put it into numerical values, which is, like I said, one number before what it is in the alphabet. So 18, 19, 14, 15, 15, 14, 11, 11, 20, 19, 8, 14, and 13 would be stop pollution, but in numbers. Our encryption, we use a function of f of p equals p plus 4 mod 26. So for p, we would substitute our value 18, 19, then 14, 15, and so on and so forth, so we can get this new value right here by using this function. For example, I'll work one, and so you guys can know how it works. So f of 18 would be 18 plus 4, which would give us 22, mod 26. So mod 26 is practically saying to give us the remainder. So you can't divide 22 by 26, so the remainder would be 22, which is what I have here in the first value. Then we switch it over to get us what this would be in numerical value, which is 1 less than what it is. It's difficult to explain. So 22 would be the next letter to, so whatever letter value is 23, then that would be our letter, which is W. So here we have it. I worked each one of these out, and this is what it gave me, and that's how we encrypted stop pollution into this. So that's 2A. 2B was much the same. Stop pollution was used the same, but they gave us a different encryption value. Once I got through that, our letters that we got were N, O, J, K, K, J, G, G, P, 0, O, O, J, I. 2C, same thing. Stop pollution was the word that we needed to encrypt, but with the encryption of f of p, 17p plus 22 mod 26, which we did that just inserting 18 times 17 plus 22 mod 26, which gave us these numbers right here, which converted to letters were Q, H, A, R, R, A, B, B, Y, H, C, A, J. Question 3 is word the same. We just got a different word. The word given to us was watch your step, and we needed to encrypt that. So again, I converted it into numerical value, then ran our function to convert it into these numbers, and then those numbers converted back into letters. I'm not going to go into too much detail because I don't want to bore you guys, because it's very repetitive. You do the same thing, just run it through the function, then turn those numbers back into letters. So here's the values for B. We use the same watch your step, which are these numbers up here. These are converted, encrypted, using this function, which was 14p plus 21 mod 26, gave us the letters R, V, B, X, P, T, J, P, Z, N, B, Z, X. And C, same thing, watch your step. Here are the numbers for that. Our encryption was -7. I'm pretty sure I missed our P there, so let's go back in the book, see what it was. Number 3, C was -7p, so let me write that in really quick and we'll come back right back to it. Alright, coming right back to it. So now we have -7p plus 1 mod 26, which is the same. 22 times 7 plus 1 mod 26 gives us 3. That, all of this was run through our function, then encrypted, and changed into letters right here. So 2 and 3 were similar. Now comes the decryption. Decryption can be a little complicated if you don't know how Caesar's shift works, or Caesar's cipher, excuse me. But once you get the hang of it, it becomes fairly easy. So, question A, the encrypted message was EOXHMHDQV, which we converted into numerical values of 4, 14, 23, 7, 12, 7, 3, 16, 21. Our decryption key, which is Caesar's cipher, is P minus 3 mod 26. Why I did minus 3 is because Caesar's cipher uses a plus 3 to shift those values 3 ahead. So this is what they got, shifting the values 3 ahead. Now we need to shift them 3 back in order to get to the original message. That's why it's negative. Minus 3, sorry. So we ran each of these numbers through our function and got these numbers right here, which EOXHMHDQV translates to blue jeans. Fairly simple. I did the same over here using the same thing, Caesar cipher, but reverse, I guess you could say. So WRGDB translates to test to date. And finally C, we got HDWGLPVXP translates to these numbers. Our decrypt key or decryption uses this function, which is the same one we use for B and A, which gives us eat dim sugar, or some, sorry, I don't know where I got sugar. Anyways, that would be it. That completes our homework 4. I hope you learned something today, and if you have any questions, just leave a comment. And I appreciate y'all guys for watching. Thank you very much, and see you in the next one.